Yesterday we talked about volumes of revolution, right? Disk method and washer method. Today we're going to look at the last method pre-AP test of calculating volumes. So click and closed, have a look at this. You get plenty of work time on this stuff after Tuesday. So this is what we might call the method of slicing or cross sections. So what does this do here? What is this method? How is it useful? How is it different than what we did yesterday? Okay, the stuff we did yesterday, why don't everybody go ahead and click these close? Is there stuff from another class that everybody's got it, just absolutely got it? You're fine. That people have to get done. Are you almost done with that, Maria? Okay. The stuff we did yesterday, volumes of revolution all have rotational symmetry about some axis, right? Does that make sense? I mean, they're all going to be, they're like things that could be, you guys know what a lathe is? A lathe is just it's a machine that it spins some object, and then you can come along with a tool and kind of carve the object as it spins. So it creates, like, you could do candlesticks or stuff like that, right? That's something that's going to have rotational symmetry. So if you set it on its base and spin it, it looks the same, right? Volumes of symmetry all have that type of symmetry, right? They have rotational symmetry about the axis that goes right down the middle. But what if we want to calculate the volumes of some other shapes? Well, sometimes we need three-dimensional calculus, right? But there's another class of problems that are simple, where we don't need higher, multi-dimensional calculus, but they still don't have rotational symmetry. And those are volumes we can calculate by slicing. So the idea behind slicing is to cut a solid into thin slices using planes perpendicular to an axis. And we'll look at an example in a second, a couple examples. And then to add the volumes of all the slices up, just like we did yesterday, right? We're going to integrate dV, that whatever the volumes of these little slices are. Slicing relies on the fact that the area of each cross section obtained by slicing can be expressed as a function of the position of that slice. So for example, if we're making our slices perpendicular to the x-axis, then the areas of those slices should all be functions of x. Or if we're slicing perpendicular to the y-axis, they would all be functions of y, okay? And so we just end up with a really simple equation for volume by slicing. The volume is just the integral of a of x dx, where a of x is the cross-sectional area of an individual slice, okay? So let's look at an example. What about one like this? So a solid has, and let me preface this by saying, these questions, I always call these coffee table questions, because these are questions like, if you have a glass top coffee table, these are all shapes you could build by setting the base down on the planar flat coffee table, right? So the coffee table is always the XY plane. You'll see what I mean. A solid has a circular base of radius 3, and the volume of the solid, find the volume of the solid if every plane cross section that is perpendicular to a fixed diameter. Okay, so what do they mean by that? A fixed diameter. If we set this thing down on the XY plane, we can set it any place we want to, right? We'll pick the most convenient place so that we can add up this volume most easily. We'd set it down so the center of our object, the center of the circular base, is right on the origin, right? So if it's right on the origin, then the x-axis is going to cut through this thing and cut it exactly in half, and so is the y-axis, right? So both of those are going to create diameters, right? They're going to cut right through the center of the circle, all the way through the circle, okay? So when they say cross sections perpendicular to a fixed diameter, I mean, that's really a complicated way of just saying perpendicular to a fixed diameter. How about perpendicular to the x-axis? Are equilateral triangles, okay? So what's that mean then? That means that any slice through this object perpendicular to the x-axis, if I slice this thing and extract the slice, it's just going to look like an equilateral triangle, okay? Make sense? Okay, so if we look at this in the context of our base, so now we're looking up, we're on the floor looking up at the bottom of the coffee table. This is the circular base where this thing is sitting on the base, right? We're looking up at it. If we look at one slice, so this is the x-axis, right? That's the x-axis. So we'll make that the y-axis. If we make one slice perpendicular to the x-axis, that's what it would look like from the base. If I take that thing out and turn it so I can see it, what's the shape going to be again? Equilateral triangle, we said, right? Every slice through our solid object, if I take it out and look at it, it's going to be an equilateral triangle in cross section, right? Okay, so if it's an equilateral triangle, we should be able to calculate the area of that equilateral triangle just based on the width, shouldn't we? And the width of the triangle, we're looking at the base right there. Everybody see that? Okay. So then what is that? We'll call that S for side. Thank you. What's that for? Well, that's not one of mine. What? Huh. Well, we'll get back to that. So if we call S of x the length of that side, right, the side that's sitting on the base, that's going to be a function of x. What's it? How am I going to calculate that? So the circle has a radius of 3, right? What's the equation of a circle centered on the origin with a radius of 3? Yeah, just x squared plus y squared equals 3 squared, right? So x squared plus y squared equals 9 is going to be a circle centered on radius 3, centered on the origin, right? Okay, so if I were to solve this for y, I just get y squared equals 9 minus x squared. So if I square root to solve for y, I'm going to get the blue semicircle, which is the equation y equals the square root of 9 minus x squared, and the red semicircle, y equals negative the square root of 9 minus x squared, right? So if I want to calculate the length of that cross section, what's it going to be? Yeah, right. It's just going to be 2 times the square root of 9 minus x squared, which we could get either by just doubling that, which is fine, or we could do the blue, the blue value minus the red value, right? Either way, blue minus red or just doubling the blue, I get the same thing. 2 times the square root of 9 minus x squared. So really we're done almost. I mean, from here on out, it's just solving an integral. We got the side length as a function of x. Now all we've got to do, well, actually we're not done, but now we've got to calculate the area as a function of x, but that's all based on the length of that side, right? For an equilateral triangle, just to make things a little simpler here, I'm going to share a formula. This is a good one to know. The area of an equilateral triangle is equal to the square root of 3 over 4 times a side length squared. That's just a formula. It's nice to know. You can always derive that pretty easily, but that's a good one to know. Okay, so the area as a function of x would just be the square root of 3 over 4 times s of x squared. Okay, well, s of x squared, that's actually a pretty convenient thing to do, isn't it? Because we're squaring 2 times a square root. So I get 4 times, and I undo the square root, the 4's would cancel. So I get square root of 3 times the quantity 9 minus x squared. Okay? So that's my area of each individual cross section. What is the volume of a slice going to be then? Well, the volume of a slice is just going to be the cross-sectional area, right, times dx. Everybody see that? Okay, and then we're just going to add all those up. Now I have a little visual here that helps, and I'll share all these with you. I'll get this all out to you before the weekend, but today I'll share a doc with you that's got all the links to all of these little things that I help you visualize stuff. Pretty sure I did this. Hopefully I did. Yeah, there it is. Okay, so if we look at this object, oh, that's the wrong one. Here, we can just fix it real quick. So why did it do that? Darn it. So we've got the upper function is square root of 9 minus x squared, and the lower function is minus that. Okay, so there's whoops, what am I doing? What did I do? Oh, there we go. Okay, and we want to have this thing, we're going to add up the area from -3 to +3. And so let's see, what did this do? Oh, this is all messed up now. And they're supposed to be equilateral triangles. Yep. So we want to do those. Okay. And then if I make, I don't know where the axes went. I used to have the ability, oh, there they are. I can do that. Okay. So there's the x-axis. There's the y-axis. And what did I do here? Did I make this go? Okay, good. So there, that's maybe that we can see it there kind of, right? So as I slide these things across, see what I'm doing now? This is the left view is if we're looking up at the bottom of the coffee table. And as we slide, as we cut slices across this thing, those are the slices. In the middle, you can see the corresponding three-dimensional slices then, right? Does that make sense? See what we're doing there? And if I show you the solids, it just looks like that. When I put all those together, it creates that shape. Okay, everybody see that? Kind of how we're putting all those together to create that shape, okay? Okay, so you get the idea there, right? So then the volume is just of each individual piece. Again, it's just going to be the area of the equilateral triangle times dx, and we'll just sum all those up with our integral. Okay, right? There's each individual piece of volume dv is just a of x times dx, which is that, right? There's a of x, there's dx, and so we're going to take the integral of dv as x goes from -3 up to +3, right? So we get this integral. Now, what do you notice about the integrand there? We have symmetrical limits of integration. We could use our trick on this one. They don't use it in the textbook, but I guess we're just smarter than them. What's our trick? Yeah, it's an even function, right? The integrand's an even function. So if we integrate an even function over symmetric limits, we can just double the volume from 0 to the top limit, right? Makes it, and that's good because it's really good to evaluating this thing at 0 is going to be great, right? The function's going to be 0, so that's a great trick. So we get 2 radical 3 times this integral. Well, that's just 9x plus x cubed over 3. Plug in 3, and you end up getting, when the dust settles, you get 36 radical 3, which is the right answer. Okay. Does that make sense? Yep.
How did you know that? Or the square root of 3 over 4?
I gave you guys that formula. That's just a geometric formula. Yeah. Yeah, the area of an equilateral triangle is square root of 3 over 4 times the side length squared for an equilateral triangle. Okay. Okay. Give me questions on that. Okay. Does that make sense what we're doing? Give me 1 to 5 on that. How are we doing? Okay. Okay. Questions. Would it help to see another one? Is that probably the next thing we want to do? Okay. Let's look at another one. How about this guy? Try another one. So let's take region R. So what is region R? Region R is in the xy plane, it's bounded by the graphs of y equals the square root of x and y equals 1/8 x squared. Okay, so it's that region that's bounded by those two curves. And we're going to cut this thing. Well, okay, so we're going to try this time cutting it parallel to the y-axis, right? So if we're going to cut this thing parallel to the y-axis, here's the x-axis. What the heck am I doing here? Why are we... Okay, yeah, well, let's do it parallel to the x-axis, right? So there's what the base looks like if I'm, right? If I'm looking up at the coffee table, that's the xy plane, and the shape is sitting, that's its base sitting on the table, okay? What do they tell us about the kinds of shapes we're building? Okay, these are squares this time, right? So each cross section cut perpendicular to the x-axis is a square, okay? So there's the base of the square. Well, that's a pretty convenient shape for us because whatever s of x is, I'm just going to square that to get the area of the cross section. But we got to figure out what is the side length, right? What's the side length then of the square, right? S of x. Well, that's just going to be the blue function minus the red function, right? The top function minus the bottom function. So the square root of x minus 1/8 x squared, right? That's going to be that length of the slice, okay? So the area then is just going to be s squared. So if we do all that math, we square that out, we're just going to get that. Okay, just trust me. I mean, it's just a bunch of, foiling something out. No big deal. We don't have to worry about the algebra. So we get that function. Volume then is just going to be the integral of a of x dx from where to where? Well, we're cutting it from x equals 0 up to x equals 4. Okay, those are the intersections, right? 0 to 4. Okay, so if we do that integral, then the integral of all this stuff, we just integrate term by term, and we get you a question. Say it again. You can continue finishing. Okay, so if we just integrate this term by term, right, then we're going to get these answers. We're going to evaluate from 0 to 4. Okay. Here, just tell them to email me, and I'll so does that make sense? Okay, we good there, right? We just did this integral. After we set it up, we evaluate it, and we get 72/35. Okay, the integral part's not very hard. Setting it up is the part I want you guys to see. So what's that look like then? Well, each little individual piece, right? If that's s of x, then the base is just going to be a square that's that squared. Yes, sir. So when you're trying to find s of x, mm-hmm. Is it from the right there? The y, so the very top function? Yeah, that's all it is, right? Mm-hmm. Yeah. If we're slicing perpendicular to the x-axis, right? Perpendicular to the x-axis, then we're just trying to find, so a vertical line that's cut through our base, we just need to find out, well, how long is that? How long is that, right? That the portion of the slice, the vertical slice that's taking place inside our base, we need to know what's the length of that slice because the area of the cross section is going to be related to the length of that slice, right? Like a radius or something. Mm-hmm. Yeah, so right, exactly. So now what if we were from yesterday, if we were going to revolve this around, let's say, the x-axis using the washer method then, right? So what would we have done there? Well, then we would have had the outer radius, right, squared minus the inner radius squared. That's a little bit different, right? Does that make sense? Okay. Yep.
Do you think they use this stuff to find like the volumes of like sphere, like the volume?
You do. Yeah.
Prove it?
Say it again.
To like prove it?
You can, like, some of the things I remember is like when you're trying to find um, centers of mass of objects that have non-uniform density or something, then you've got to do some integral, three-dimensional integral, that's weighted by mass or something, and to find the center of mass of an object. But if it's uniform density, then you can just use these kinds of things. Yeah. Okay. You can just use these for complicated shapes. Okay. Um, we're not really going to get to that stuff this year, but it's not that big a step in the future when you do that stuff from what we're doing right now. I promise you, it's really not that big a deal. Okay, so what would this look like? Let's just take a quick look at, I think I have something here. Do I not? Yeah, I do. Okay. Right, so there's, oh, that's the other one. Okay. Yeah. All right, so there's that guy. If we wanted to do this about the y-axis, we would have to change things a little bit, right? If we wanted to the y-axis, then that means now we're going to have to find this distance, and so we have to treat these as functions of y instead, right? So all we have to do is just go to our last example and solve for x, right? If I solve for x in the blue shape, I would just square both sides. I get x equals y squared, right? And that's just going to be the sideways parabola, okay? If I solve for x here, I would multiply by 8 and then square root. So I'd get x equals plus or minus the square root of 8y. Okay, and we'll just take the plus one. So then that would look like I get those two shapes, right? There's the blue function written as a function of y, right? There's the red curve written as a function of x, okay? And if I want to find the length of that cross section perpendicular to the y-axis, well, then I would just have to do, now this becomes the top and that becomes the bottom, right? Because we're looking on it sideways instead of up and down now. So the length of that slice would be the red value minus the blue value, okay? So now the side length as a function of y is just that, okay? And if I want to calculate the square that I'm going to get, the area of the square when I pull that slice out and turn it so it's square, it's just going to be s of y squared. So that whole thing squared. And again, if you just do all the math, if I square that thing out, I get that. The volume is going to be, a piece of volume is just the cross-sectional area, right? So s of y squared, which is that thing, times dy. And then we just integrate that. Only now, instead of going from 0 to 4 like we did with x's, because we're making our slices perpendicular to the y-axis, they start at y equals 0 and end at y equals 2, okay? So we integrate from 0 to 2, and if you do that integral, integrate term by term, you just get 144/35. So it's a different area, right? It's bigger. We'll say it again, or different volume. Yeah, it is because it's a different shape. Look, I'll show you. It's a different shape. The one we looked at looked like that, right? that make sense? Like that's the one when we slice perpendicular to the x-axis, it looks like that. Now look at what happens if you slice perpendicular to the y-axis. This one was kind of hard to do, and I had to cheat a little bit, but here's what it looks like. Pretend those are y's. Like, so now this is, you have to cheat a little bit here. So this is the x-axis, and that's the y-axis, right? Look what happens to these shapes. They get much bigger because that's a bigger distance, right? So you get bigger, right? Looks like that. See the difference between that and that? What's that? Yeah. Let me get it so you guys can kind of see the two next to each other. See, that's different than that is, right? If I spin that, it's hard to, not very good at that, but you get the idea, right? Right. Anyway, you get the idea, right? Okay. So it's different. All right, what about, I think I got one more to look at here. What about one like this now? Okay, this is a little different one. This is one where if we wanted to, for example, prove what the volume of a right square pyramid is, so it's got a square base, and the apex is located right above the center of the base. How could you do that one? Well, this is not a coffee table problem because this one doesn't sit, its base, we don't really worry about its base. We just know that if I am going to start at the origin and we're going to let the x-axis go right down the center of this pyramid, right? That's okay, because as long as I can predict the cross-sectional area as a function of x, we're fine, right? So if they tell us that the pyramid has a height of h, so then from the base, like this pyramid, if I pick it up and set it down on the coffee table, we're going to be looking at a square base, right? Different kind of problem. And then it's going to, there's going to be an apex, a pointy apex right above the square base, okay? Just like the Egyptian pyramids have square bases, don't they? I think they do. So there's just like a Egyptian pyramid, right? So the height is h, the width of the base is b, right? So our axis actually goes down the center of that thing, right? So here's the x-axis. If we look at this thing in cross-section, so we're looking like there's the y-axis and there's the x-axis, and the z-axis comes straight out of the board. That's a cross-section of this pyramid cut right down the middle, right? So there's my h, there's my b. If I look at an individual cross-section that has a slice of width s, how are we going to figure out what that length is? We'll just use similar triangles, right? We know that that little triangle right here is similar to the big triangle right there. And so the ratio, because of that, we could say that the ratio of b over h is equal to s over x, right? Because we're putting the tip of the pyramid right at the origin. So that distance is x. Okay, everybody see that? So if I solve for s is going to be equal to b over h, those are just constants, right, times x. Okay, so the width of each individual slice then is just going to be b over h times x, right? And the cross-sectional area is a square, right? Where that's going to be the width, see s right there? S is the length of one side of that square cross-section. So a of x is just going to be that squared, s squared. Okay, make sense? So then when we set up our integral, what you guys tell me, what's our integral going to look like then? Well, what's dv? What's a little piece of volume going to look like here? What is it going to be?
S squared O times.
Yeah, S squared, exactly. So S is B over H times X squared, right? That's our cross-sectional area. What's the thickness of a slice? Dx. Yeah, it's thin, right? It's infinitesimally thin. Okay, and then we'll just add all those up, right? So we'll take an integral. The total volume is just going to be the integral. That's what it looks like an S. The integral of B over H times X squared dx from where to where? Well, we're going to slice this thing from x equals 0 up to x equals what? H. That's it. Exactly, right? So if we do that integral, then if I square all this stuff, I could pull the b squared over h squared out front because those are constants. Times the integral of x squared dx from 0 to h. That's a pretty easy integral, isn't it? So we end up with b squared over h squared times x cubed over 3 evaluated from 0 to h. Well, at 0, that's going to be 0, right? But at h, we're going to get h cubed over 3. Okay. Right? Everybody good with that? Okay, so then what's that going to give me? Well, I could cancel some h's, and my final answer looks like 1/3 hb squared. That's it. That is the volume of a right square pyramid. We just figured it out. Okay. Yep. 1/3 the height times the base squared. What's that? Well, you could do that without calculus.
That's how they made the pyramid.
Yeah, exactly. Yeah. Okay. So, I mean, I don't know if this is worth doing. I mean, you could show here that, like, how would you calculate the volume of a right circular cone? Volume of a right circular cone. We would probably rather use volumes of revolution here, use the disk method than anything, right? You could do this though. The disk method is just a particular instance of what I just showed you, but because of the symmetry, we can use revolution instead of using cross sections. But we could also do this by cross sections, couldn't we? Right? Because the cross-sectional area as a function of x is just going to be pi r squared of those circles, right? Okay, and if we, again, if we used similar triangles, well, if we know that the height of our cone is r, the height is h, and the radius of our cone is capital R, well then look, we could just solve for r. That's what we need, isn't it? Right? The radius of a cross section then would just equal, what do we get? The radius of a cross section, little r, would just equal big R over h times x, right? And so we could just integrate then. We would just do pi times r squared. Well, there's r squared right there, right? Pi r squared times dx, the thickness of each slice, from 0 up to h. Okay, we can do it that way too. Make sense? Okay, how would we set this one up? This is good little practice here. How would we set this one up as using disk method? Right? That would be our slices. So we would just do what? Pi times the integral of what? Right. We're just going to add up the volume of disks. R squared dx is the volume of a disk, right? Okay. So r squared, which is that stuff, dx from 0 to h. What do you know? Same integral. How about that? Right? Because by the disk method, don't we just get this? Volume by disk is just pi times integral of the radius of the disk squared dx from a to b, right? So those two are the same thing in this case because of the symmetry. Okay? Good? All right. So maybe the last thing I'll do, I just want to backtrack a tiny bit here. If I go back to slope fields, and let's just look at a couple of these we didn't get to. Let's just like practice on a couple of these. How about this guy for the remaining time? Which of the following differential equations could have the slope field shown in figure 7? How could you pretty quickly like analyze this? You notice anything interesting about that slope field? Yeah, look at this right here. See, look at this right there, right? The slope is 0 at x equals 0, right? And it doesn't depend on y. You know, something else you notice is that you look at any column and the slopes stay the same, right? So the derivative should only depend on x. So we can immediately cancel those guys out, right? Does that make sense? And then let's see, which one would it be? Well, it's just going to be this, isn't it? Because we need it to be positive to the right and negative to the left. So it's just that. See how that works? Okay. How about, you had a question on that one? No. Yikes, huh? Okay, look at this one. What are some things you notice about this that are interesting? Well, okay, for one thing, you notice that, what do you notice here? You notice that you get, so what are some things you could do here? What do they want us to do? Oh, they want us to say whether these are true or false. The graph of the particular solution that satisfies f of 1 equals -1. Well, that's just the ordered pair. Look at that. What's that mean? That's the ordered pair 1, -1. So if I go over to 1, -1, that's right about there, right? Is concave down on the interval between 0 and 2. Yeah, we can see that because look, if I look at a trajectory that goes through that point, doesn't the trajectory go like this, right? So it is concave down. That's true. You can just see from what a trajectory would look like through the slope field there. That's all you have to do. That's true. Okay, the graph of the particular solution that satisfies f of -1, 1. Okay, so what's that one going to be? That's the point -1, 1. So -1, 1 right there, well, that's going to be concave up. So that's true. Okay, make sense? The graph of a particular solution that satisfies f of 0 equals 0. Whoops. Oh, come on. Green. There we go. So right there, well, that looks like an inflection point, doesn't it? Okay, look, because it's going like that. So is that concave up on that interval? No, it's not. It's concave up on that part, but it's concave down over there. So that's false, right? Everybody see that? Concavity is changing there, okay? Concavity must be 0. And then last one, a point of inflection. True, it is a point of inflection. Okay, right? I'm going fast. Any questions on that? Okay. Let's see. How about one like that? Okay. What do you notice here? Which of the following could be the particular solution to the differential equation satisfying y of 0 equals 0. So right there, okay? Well, what do you notice here? This thing has a horizontal tangent at 0, and it looks like it's doing something like that. Okay, so which one of those functions would do that? Not that one, right? Why not b? Because what would e, an exponential minus, what's an exponential function look like? Just goes up, right? Okay. Oh, it's e to x squared. So actually that could be it, huh? X squared. Because if we pick positive values of x, it's going to be increasing, right? We're going to get increasing values. So minus 1. Uh, it would be, okay, the other thing would be this guy. Look, I'll show you, if we graph that one, I'll show you what it looks like. If I graph that guy. If we graph y equals e to the x squared, because that's being squared, look what happens. See, it does that, right? E to the x squared minus 1, it does go through, right? So it does go through the origin. What you'd have to do is just maybe look at some slopes too. But the rest of these, if you think about what the rest of these look like, they're not going to match that. If I did negative cosine x plus 1, that's the same as 1 minus cosine, oops, I can't type, cosine x. On R, that actually could be it, couldn't it, right? Okay, these are going to be probably two biggest slopes on the red one. And what do you do? Like if you're trying to debate, the rest of these aren't going to match it. So it would be between those two. What you could do here is you could take a derivative. Y prime equals what? Well, we're just going to get 2x e to the x squared, right? And on this one up here, we're just going to get y prime equals sine x. Okay. If I plug in some values, like what if I went back to go to 1? If I go to the point 1, like if I plug 1 into the function and I find the value of the slope there. If I plug 1 in here, the sine of 1 is going to give me some value that's going to be, what's the sine of 1? Pi halves is like, what's 1 going to be? That's going to be like close to pi thirds, right? Sine of pi thirds is going to be square root of 3 over 2, right? So it's going to be a little bit bigger than 1. That's feasible for that, isn't it? If I plug in 1 here, I'm going to get 2. That doesn't look like 2, right? If I plug in something like negative 1, here I'm going to get negative 2. What if I plug in 2? If I plug in 2, here I'm going to get sine of 2 is a reasonably small value. Here, if I plug in 2, I'm going to get something pretty large, right? Really, really big value. I'm going to get 4 times e to the 4th. That's a huge, really, really steep value. And we don't see that slope being that steep at 2, right? So this one is not, I mean, this would have to be the cosine one. That's kind of a tough one. That's a little tricky. Okay, what about this one? Real quick. Oh, we're out of time, but what would you look for here? Vertical tangent at 1, it looks like, right? And it looks like there's a horizontal tangents at -2, and 0. So you just find the one that has where the derivative is equal to 0 at 0 and 2, right? And the one that's going to have a vertical tangent line at -1. Well, I think all those those three have vertical tangent lines at -1, right? But you'd have to find the one when I differentiated it where the slopes are equal to 0. See what I'm saying? How that would work?
But B would have 2 asymptotes.
B, you're right. B would have 2 asymptotes, and that one doesn't. So you could cross that one out. Then you got it narrowed down quite a bit. Yeah. It is Monday. Yeah, it is Monday. Yeah, I sent some out to them. Yeah, so Monday. So just be there. Testers, be there at 7:45. Okay.
What are we doing on Monday while they're testing?
You just working.
Okay.
Yeah, and then I got one more thing. I'm gonna show you guys one thing on Tuesday, and then you're just working, and I'm gonna help you through. You're gonna just work and get questions answered for the rest of the year and finish testing. Yes. Yeah. Hang on to that. Yep.